Welcome, everyone. A fantastic response to another of our COVID-inspired stay-at-home webinars on construction history topics. At least where I am in Minnesota, it's a great day to talk about bridges. Cool, crisp outside, sunny, great fall day. This all came about in light of the collapse of the Scott Key Bridge in Baltimore that inspired this topic, covering over 200 years of bridge building and the innovations that inspired it. So I'm Peter Hilger, past president of the Construction History Society of America and host of this webinar as faculty director of the Construction Management Program at the University of Minnesota, with a passionate interest in all things history. I am joined today by my CHSA board colleague, Ms. Alicia Svensson of Northeastern University, a PhD candidate in history, who will serve as moderator and will present your questions. We will take questions at the end of all three presentations, and we can go past our appointed end time, but we may insert a few questions during our speaker transitions. So enter the questions as they come to mind, and we'll try to get to all of them. In the background is my associate, Mr. Paul McClagan. He's manning the Zoom controls, producing this podcast that will be recorded and placed on our CHA website for posterity. If you're having technical issues, use the chat button, and Paul will try to answer your questions directly. So I am also joined today by our panelists, whom will address your insatiable need for history. I will let them expand on their personal introductions when they present. But we'll start with Bob Dermody. He's a professor of architecture at Roger Williams University in Bristol, Rhode Island, teaching undergraduate design studios and graduate courses in the design of structures. Robert holds a bachelor's degree in civil engineering and a master of architecture degree with a concentration in structures from the University of Illinois at Urbana-Champaign. He's also a founding member of the Building Technology Educators Society and is a registered architect in Massachusetts. He will discuss an early chain suspension bridge in Newburyport, Massachusetts. I'm also pleased to have Mr. Ulrich Boying, is a retired German-born architect and monument conservator in Germany, beginning in 1980 until his retirement in 2013. He's coming to us today, this evening for him, from Stuttgart and Karlsruhe, Germany. He will convey an interesting and innovative way a bridge was constructed over the Rhine River using muscle power and a likely good measure of German ingenuity. And finally, I'd like to introduce Ms. Katie Haun Schuring and her colleague at the Minnesota Department of Transportation, Mr. Chris Hoberg. They will discuss the 3rd Avenue Bridge restoration in Minneapolis. Katie was a historian with the Minnesota Department of Transportation, and she holds a master's degree in historic preservation from Ball State University. She led the Cultural Resources Unit and was the project historian on the rehabilitation of the 3rd Avenue Bridge project in Minneapolis. Chris was MnDOT's project manager for the 3rd Avenue Bridge in the pre-construction phase and the project engineer for 2 years in the construction phase. He comes to us with 15 years of experience with the Minnesota Department of Transportation, having spent time in bridge inspection, bridge scoping, project management, and construction. And he's an alumni of the University of Minnesota's Civil Engineering program and is a licensed engineer in the state of Minnesota. So with that, I've introduced our team, our panelists, and with that, I'd like to pivot to you, Bob, to get us started with the oldest bridge on our docket today.
Great. Thank you, Peter. I'm just going to share screen here. Oh, don't look at those just yet. There we go. Can everybody see that title slide?
Yes, we can.
Great. Thank you, Peter, for that introduction. One minor clarification. My undergraduate degree was from the University of Massachusetts at Amherst. So I studied civil engineering and then got into architecture. But I have a love of bridges. So I want to tell you the story about the Newburyport Bridge up in Newburyport, Mass., which was an early chain bridge. And I was telling Peter recently how fascinating a project this was. I had heard about chain bridges. I didn't understand completely that it was literal chain links that suspended this bridge. So there's the image without the text. So you can see the beautiful setting of the bridge. It's about a 244-foot span. I'll get into more details about the other dimensions later. But it's significant to learn about why this bridge got built here, and the use of this materials, and why this type of system was built at this time in this location. So quick context for you. We're located just about 40 miles north of Austin. Oops, sorry. There we go. So the bridge is located in that red circle on the Merrimack River. So it spans from Newburyport, Mass, into Salisbury via Deer Island, that small island in the middle of the river. So there's another bridge on the other side. I'm going to focus on the chain bridge. Route 95 has a modern steel tied arch bridge, and there are other bridges downstream, which is significant. So sort of a veritable confluence of bridges here. And also, interestingly, I think it does play into the materials and how they were constructed for this bridge, not far from the ports of Salem and Portsmouth, which we'll factor in later. So a little bit about the chronology of this location. So there have been bridges at this site for over 230 years. The first one opened in 1792, which was timber, which is common material for bridges of that era, but they didn't last very long. They couldn't survive the natural elements, the cold winters and the rain and the salt, etc. So in 1810, a chain suspension bridge was built, closely modeled on a patent from James Finley from the Philadelphia area, who first built those types of bridges. He built about 10 of them in Pennsylvania. In 1827, fairly early in its life, there was a partial collapse, and this happened in February. There was noted to be heavy snow and ice on the bridge, and also simultaneously some farm animals were being driven across it, some oxen and horses, and the confluence of that all caused the bridge to collapse. However, it was rebuilt in kind, so they just replaced the change, which my sense is they believed in the system, but it was just due to primarily the heavy snow and ice. The bridge did last until 1910, but it evolved, and I'll try to show you some images of that. And then it was replaced with another suspension bridge, but it switched to a newer system, wire cables, and it was actually done by the Roebling brothers of Brooklyn Bridge fame, which had just opened not that much earlier. So the chain bridge lasted 100 years, which is a record at the time. And for over 200 years, there has been a suspension bridge in this location. So a quick image of the prior bridges. This is looking east downstream of the Merrimack River. Timothy Palmer, who was a local housewright, built some wooden arched truss bridges with props underneath. The location of the chain bridge is on the right side. This text here is captured from James Finley's patent application or description, and I've underlined some key terms here. He's interested in safety, simplicity, economy, and duration for these structures. And these certainly remind me from my architectural education of the architecture principles from Vitruvius of firmitas, unitas, and venustas. I also note there the simplicity is perhaps something we could use in our modern structures. This is an image not of the Newburyport Bridge, but of a chain bridge of this time from Finley's patent application. I just want to point out some of the key features of any suspension bridge, which interestingly have really not changed over time, the basic components and forms. But what has changed are the materials and connections and ways to stiffen them. So primarily, the components include the abutments, which were obviously stone at this era and were for a very long time. And then timber was used for the towers on top of the abutments and the deck. And then the iron chains, you can see the main chain from the tower top to tower top. And then there were vertical chains from the main chain to support the deck, and those are called suspenders. And just below here, I highlight in red the cross section of the chain. So the chain lengths were about 2 feet long, and they were square in cross section, maybe about 1.5 inches on a side, so not very big. But those were strung together, and we'll see in later drawings how those were specifically designed for the stresses they expected. And in the center is a saddle of how the chain would work over the top. And it's interesting, they use a separate piece for the curved portion of that because they didn't want to bend the actual chain link itself. So this is a wonderful image showing the chains in action on the Newburyport Bridge. And you'll see that there are 3 on the far left, there are 3 on the far right, and then there are 6 in the center. So there were 3 each for the spans on either side. There were individual passageways on each side, separate portals. The tower here is a good shot too of the beautiful shingle covering the timber framing, a classic New England shingle style. Also, you can notice train tracks. So there were electric trolleys added to the bridge much later, which was very interesting because of the increased weight those brought, but also the dynamic movement of that trolley car over the bridge. And that was one of the challenges for early bridge builders was stability. Strength was not as much of an issue, but stability and stiffness due to dynamic loads from the farm animals, as I mentioned earlier, from trolley cars, and also from wind from the side. This image also shows something very important about the chains. So the chain out over the center of the span is a catenary curve, and that comes from the fact that the vertical suspenders are evenly spaced, and that helps work with the deck. But the backspan chains, as you can see on the right side of the photo there, have no vertical suspenders, so they're straight. And that also shows the understructure. That deck is not supported by the chains, but it's supported from below by timber framing. And you'll notice one dark timber frame there in the center at an angle leaning down onto the abutment, and I'll talk about that in a moment. A couple of other things to notice here in the top right side, or the middle and the top right side, you see a little stub there, and that was additional heavy timber members put in crisscross fashion to allow additional wire cables. So wire cables were added before the bridge, the end of the life of this bridge, because that was the side where the trolleys were, which they understood the heavier load, so they added extra wire cables. And then at the very top, very thin lines were the electrical cables. Also notice the form of the 2 portals with the center wall. So I found this drawing in the research. It was a beautiful drawing of the record of the structure of this building. So on the far left are the longitudinal sections, and on the far right are the cross sections in elevation. So you see in the left the timber framing used inside that it was covered. So the covered bridge aesthetic from New England, and that knowledge was brought into bear here. On the lower left, we see the timber framing inside the abutment. And these are direct relations to other constructions in the area. So timber framing from barns and large churches, the shingles on top of it, the covering from covered bridges because they understood they had to protect the wood. Lower left, these are very similar to piers that we built along the New England coast using heavy timbers with rocks inside them called cribs. On the right, a couple of things to note from Mr. Finley's patent application. The chain at the top wants to have the same angle on either side of that tower. So in fact, in this drawing, the chain on the right should be straighter because that's the one without the backstays. I mean, without the suspenders, excuse me. The significance of the equal angles relates to the structural principle of ensuring that the resultant vector, the compressive force from the tension in the cables, would go straight down into the tower. And that provides stability and stiffness to the tower as well. And you'll see the tower is the 2 outside timbers, but also a center one, which would take that force right down into the abutment. And then in the lower right, you can just see a little diagonal. That's the strut that we saw in the earlier photo to help hold up the backspan using the abutment so they didn't have to go all the way to the ground at that location. And it's an angle providing some stability as well. And that type of detail can be traced all the way back to the Romans, who were masters at building masonry arches using wood formwork. And there's a very similar detail that you can trace back all the way to the Pont du Gard in southern France, in Nîmes, where the Romans would build in little ledges in their masonry to put a strut to support the formwork. So it's an interesting tradition of construction coming down through the ages. Right in the center, we have a good image here. It's a little overlap with another drawing, but it shows the vertical suspender chain and how it interacts with the main chains. So this is material that would have been cast on site or forged on site from a local blacksmith. And you can see just to the left of the red rectangle there's this sort of link and how they are thickened slightly at that edge. This photo shows some of the things we've seen before, but I want to call your attention to the anchorages. And those are the large stones and blocks at the ends of the cables at the ground. And we see 2 of them here on the trolley side. We can't see the one on the far left because it's a little lower. And that was a significant part of the design as well. And James Finley noted in his patent that it would be advisable to splay out the chains when they got to the anchorages, meaning add more branches. So instead of a single chain, it would branch out into multiple chains. And that allowed more surface area to be piled over with rock. So a large pit would be dug, stone would be set in the bottom, the chains would be laid on top, and then heavier stones and block would be laid on top of that. And they may have even used some iron bolts to secure it. And it's also important to design that pit anchorage, the anchorage pit, so that the chain would come in without changing angles severely. So the force would be normal to the anchorage, which is important not to bend these chains. You want to let them work in their pure tensile capacity. And this is interesting as well. So the Cornell University got a hold of these links after the bridge was removed in 1910. So this study is from 1911, and they took several of the links and many of them and tested them. And they studied them, and they wanted to find their strength, and they wanted to find out where they might break and how they might break, and study the welds. They studied ones that were intact and ones that may have been small fractures. They studied ones that were corroded, ones that weren't. And on the right, you can see the very careful drawings showing the size and shape of them and the dimensions and their load capacities. And then also here, especially in that bottom one, you can really see the ends would be thickened right where the next link would come in. So this is early 1800s, and this is not Newburyport now. These are much bigger span bridges, but also called chain link bridges, but in a very different style. So the bridge on the left is the Thomas Telford Menai Bridge in Wales from 1825. And then on the right is the Clifton Suspension Bridge by Isambard Kingdom Brunel, 1831. But these are different, much bigger spans. But they're flat bars. And the difference with this system is you can aggregate them. You can just stack them side by side and increase the capacity and layer them. And also notice where the pins go through to connect these links, the bar itself is widened sort of into a dog bone shape. And that shows that they understood that there would be increased stress there, right where the pin is acting and bearing on the inside of the pin connection. So early 1800s, those bridges were being built, but back in Newbury, just downstream, closer to Newburyport Center, another chain bridge was built with multiple spans, and the engraving here is shown in the middle and the bottom right. So they kept with this. So that my sense is that they had a bridge that was working, and this one overlaps with the chain bridge, although I don't think it lasted as long, and I'm not sure why, but my theory is that it was a much bigger, longer bridge, much more exposed to the weather as well, and literally sort of the case of many more moving parts. And so this one did not last into the photographic areas the note there shows. So in this photo, I want to point out a couple of things. So we've seen some of this before in other images, but there's a wood frame in the center. That was for the cables for the trolley car. There's a stiffening girder under the trolley car side. And then in the very center, right over the little sailboat, you can see a curve coming down below the deck. And that's an interesting relationship that the designers have to decide upon, is the relationship of where the deck is to where the chains are. Also interesting to note here, as we have additional cables, as I mentioned, but the main chains are still there, but the verticals, now some of them appear not to be chains. There is one on the far right that you can see very close to some others that is still a chain. So this bridge was a hybrid. It had chains, it had cables, it had chain suspenders and cable suspenders and stiffening girders. So it was sort of evolving because it lasted so long. There's a beautiful postcard of the bridge, and there's lots of them. So the bridge was well loved in the community. It was painted and photographed by people. And you can see the trolley car going over. You can see the steamship. So it's a very active area. But I show this photo because I want you to compare it very closely to the next one. So you'll notice now the tower is very different. There's a single portal now. There's only, and this is 1910, so this is the new bridge. It's a cable bridge, and there's only cables on the outside of the deck. It's a continuous single deck now, still the trolley car, but also notably a very deep 5.5 feet or so stiffening truss on each side of the bridge to help stiffen the deck. The vertical suspenders appeared to be spaced a little differently than they were prior, and also much deeper cross members, as you can see, the girders going crosswise of the bridge. So here's a photograph of it very recently in today's form. The tower is still in the sort of the same mode, but not as characteristic. It's not shingled, it is concrete. It shows the single portal, but we do have riveted steel trusses on each side. You can see the paired cables. I haven't measured it or found it, but the height of this tower looks a little lower to me, which would change the span to depth ratio of the bridge. But the wire cables could handle that increased load with the lower cable, because a flatter cable would tend to have more stress than a deeper cable. But that's the trade-off in suspension bridge design. Deeper cables or a bigger sag has less stress, but therefore you have to build bigger towers. It's a very well-loved bridge. There's lots of signage there proclaiming its endurance and who built it. There's obviously some weight limits on it today. But I'd just like to close with the importance, I think, of the legacy of this and why this type of bridge wound up in Newburyport, Mass. But you had a very talented craftsman workforce of people who built barns and churches out of wood. There were Irish immigrants who built masonry structures for churches and dams and bulkheads for harbors, and blacksmith, and related to both the agricultural and the maritime industries. So those all came together, and I think it's what can be most interesting is the combination of all of those. So all of those worked in their separate industries, but it's the combination of them into this beautiful bridge that allowed it to last so long. So here is another photo just taken recently of the bridge in its setting. The setting really hasn't changed that much. The bridge has, but it still endures to this day. And I thank you very much for listening to my story of the Newport Bridge, and I'd be happy to answer any questions.
Yep. Well, we'll sort of aggregate the questions here towards the end, Bob, but that was very, very interesting.
Thank
Um,
you.
let's see. Let's bring up Ulrich now to talk about the bridge over the River Rhine.
Hello to all viewers and listeners. I'd like to tell you some facts dealing with the Niam Bridge connecting Waldshut in Baden, Germany, and Koblenz in Switzerland. Next slide, please. For a few minutes, I would like to take you to the middle of the 19th century, to Europe, southern Germany, to the Grand Duchy of Baden, and to the border of Switzerland. At that time, Baden was a sovereign state in the so-called German Confederation. Next, please. In 1840, the Baden State Railway opened its first railway line between Mannheim and Heidelberg. The railway then followed the River Rhine and reached Basel at 1855. On its long-distance goal to the Lake Constance, the track construction stopped 1856 in Waldshut. Next, please. The Swiss Northeast Railway had extended its main line from Zurich to Koblenz via Torgau since 1859. The yellow line. You see the yellow line? Next, please. In Waldshut, the railway companies planned the connection of both railway networks by crossing the Rhine over the bridge. Next, please. Robert Garbig planned construction at the age of 38 years. He was an engineer and worked since 1846 for the Baden State Railway. In Waldshut, it was the second cooperation between Garbig and the so-called Gebrüder Benckiser, who previously worked together at the Wiese Bridge in Basel, 1855, afterwards at the Rhine Bridge in Constance, 1862. Next, please. The Gebrüder Benckiser are from Pforzheim they were the leading bridge manufacturers in southern Germany between the early 1850s and the end of the 1880s. During their 40 years of activity, they were responsible for the construction of many bridges in Germany, Switzerland, and Austria. Now I have to admit that the previously announced advancement of the Waldshut Bridge was not the very first time. Between 1856 and 1858, the company used the same method on 5 bridges in Switzerland, all of which were moved over river valleys without scaffolding. The 5 bridges were therefore the first steps in a series of further developments, but in Waldshut, it was the really first time that Benckiser used this process in Germany. Next, please. The original idea of lattice trusses was patented in 1820 by Iffield Town from Thompson, Connecticut. This wooden lattice construction was later adopted to rolled iron and often used in Europe until the end of the 19th century, when it was replaced by iron half-timbered structures. Next, please. I think I don't have to read all the terms. You can see it yourself. The total length is about 190 meters or about 208 yards, including 6 massive arch openings in Koblenz. You see on the left side, the Frisk side, on the right side, the Baden side. The actual iron construction measures about 130 meters. On top, the bridge could have carried 2 tracks, but it never did more than 1. The puddle iron weighs about 530 tons, and the iron construction was assembled within 8 months from December 1848 till July 1849. Next, please. Benckiser used the later railway embankment in Waldshut to build a wooden workshop building at 22 by 27 meters. It was large enough to build the parts of 1/3 of the total length under its roof. You see the roof and the workshop right on the right side. Next, please. The whole construction was manufactured in 3 parts, successively built and moved outside the workshop, connected with approximately 33,000 rivets to lattice girders. The parts were connected between the middle of May and the end of June 1859 to the total length of 130 meters. Next, please. During each of the 3 advances, the connected parts were pushed forward outside by about 44 meters. Since there was no scaffolding over the river, 1 wooden stem beak was mounted in front of the girder. Maybe we go 1 back, please. See it in the middle. the stem beak mounted in front of the girder, and now with a back to the next one. Rather to the next one, please. This must be far. Doesn't matter. Was mounted in front of the girder. Bankiser also required a wooden auxiliary support about 37 meters away from the pillar to reduce the free floating overhang in the wide center opening. To move the construction, the company needed the strength of about 60 men divided into 3 groups standing on top of the bridge. A painting from Bern gets please one back. This is forward. Can you go one back, please? Another back. Another back. Yes, thanks. A painting from Bern on the left side shows where the workers stood upon the girders. They worked at 3 double levers mounted on both sides of the girders, and every move of the levers shifted the structure to approximately 10 centimeters. So they had to move a very long time. Between June 29th and July 9th, it finally took 10 days to move the iron bridge over the Rhine. The iron structure then had to be completely lifted in order to install the final support rollers. And now, please, to the historic photos. Forward. Yes, thanks. The contemporary photos from 1859 show the bridge under construction seen on the Swiss riverbank. Here on this first building, first photo, you can see on the left side the massive structure, and on the right side, quite on the middle of the right side, you see you can see, not very good, but you can see the iron construction coming from the right side. Next, please. Here is a view to the construction. What's the word? I don't know what the word is. Interesting is you look, you can see the wheel, the wheel on the left side, and there is a small person. So you can see the dimensions of all this. Next, please. And at 1859, the bridge was almost completed, and it was painted. Next, please. Painted by next, please. On the right side, you can see a red iron paint. On the left side is the actual paint. The white red iron paint is linseed oil and red lead, which was commonly used in that time. Bankiser. Next, please. Bankiser strived to perfect their skills in every project. For example, in Strasbourg, 1851, an attempt was made for the first time to move the 177 meters long iron structure across the Rhine using steam engine power. Since this was unsuccessful, It's about 1,000 tons had to be moved again only using muscle power. In 1859, the Waldshut-Constance Bridge was finally financed equally by the Baden State Railway and the Swiss Northeast Railway. Since this bridge is still half-owned by the latter successors Deutsche Bahn and the Swiss Railway, it is still in use as it has been for 165 years. And my last words, in 2009, Switzerland listed the bridge as a cultural asset of national importance, and in 2012, the German Monument Preservation Authority followed suit by assessing it as a cultural monument of particular importance. So we can hope that the bridge manages to stand for another 100 years or even more. Last, please. Thanks for listening.
Dankeschön, Ulrich. And I know it's a challenge for you to talk about the bridge in your native language, and but we understood. So very, very well done. So with this, we'll come to a more modern age, I suppose. Maybe 100 so years. No, not even 100 years later. So I'll turn it over to Katie and Chris. Take it away.
All right, perfect. Thank you. Good morning, afternoon, evening, wherever you're from. My name is Katie. I'm a historian with the Minnesota Department of Transportation. I'm here today with Chris Hoberg, an engineer, and we will be talking or telling the story of the 3rd Avenue Bridge. It's a graceful open-spandrel concrete arch bridge constructed in 1918, and it spans the Mississippi River here in Minneapolis, which is one of the Twin Cities that makes up the capital of the state of Minnesota. It has a unique construction history that combines its engineering challenges over in the Mississippi with the needed architectural style from the public in the early 20th century. This is a bridge that's listed in the National Register of Historic Places, and it is one that MnDOT has committed to preservation in perpetuity. All right, so let's get oriented. Here we are, Minnesota is in the Midwest. And then the bridge is located in Minneapolis, downtown Minneapolis, and you can see that its location on the Mississippi River and in the heart of downtown Minneapolis will really play a part in this history. Okay, so at the turn of the 20th century, Minneapolis was expanding rapidly. We had flour and lumber mills harnessing the power of the Falls of St. Anthony. Businesses were growing on either side of the river. To the west, Minneapolis's downtown was growing, and to the east, the village of St. Anthony was also picking up steam and becoming a burgeoning residential and business district. Politicians began discussing the need for another crossing of the Mississippi here as early as 1890. But at the time, there were only 4 crossings of the Mississippi. The first was the Hennepin Avenue Suspension Bridge. Just to the south of that, it was James J. Hill's Stone Arch Bridge, which actually carried railroad traffic, mostly freight, but also people over the Mississippi. Further to the south was the 10th Avenue Bridge, the Levee Bridge, and to the north, the Upper Bridge, which was also known as the Plymouth Avenue Bridge. So very, very few locations. Of these, the Hennepin Avenue Bridge saw the most traffic. And just like engineers today, they counted the traffic at the time. And here you can see how they were making a case for the need for a bridge. Hennepin Avenue was overwhelmed with traffic, wagon traffic, automobiles, carriages, pedestrians, compared to the 10th Avenue Bridge to the south and the Plymouth Avenue Bridge to the north. It's no wonder that the suspension bridge was seeing so much traffic because it was the only bridge that was actually located within downtown Minneapolis. Not shown in this graphic is actually the streetcar line that the Hennepin Avenue Bridge also carried and ran to the village of St. Anthony, carrying several thousand people. Today, that streetcar line continued to the east all the way into St. Paul. There was clearly a need for a second bridge over the Mississippi in downtown Minneapolis. But it took decades of debate, strife, and public requests before the Minneapolis City Council actually agreed to place a new crossing between Hennepin Avenue and the Stone Arch Bridge. The city bridge engineer at the time, Frederick Kaplan, was the designer and was tasked with making the council's directive a reality. Kaplan was a Norwegian-born engineer who was educated in Sweden and Germany and emigrated to the United States in the 1880s. He understood that the location of the new bridge was a precarious one because in this particular area of the river, there's very fragile limestone ledges. And if there was any damage to any of those ledges, it could cause a collapse to the Falls of St. Anthony and thereby collapsing the industry in Minneapolis. Okay, so what did he do? The city actually hired the concrete and steel engineering company out of New York to design a bridge. National public sentiment at the time really liked concrete arches, reminiscent of the arches in Paris, as a couple of different newspaper articles. Really, people wanted an arched bridge over this location. So the engineering company came back with this location. Kaplan immediately rejected it, and he noticed that they were placing piers on these fragile limestone ledges. So here's one in particular, right on top of that ledge, probably would cause a collapse of the falls. So Kaplan took it upon himself to actually design his own bridge. He designed a parabolic arch. It would span 435 feet across the river, only had a couple of pier locations in the river, a beautiful thing, but the public said, no, I don't want that. I don't like that. I want something more pretty. So Kaplan went back to the drawing board. He collaborated with the concrete and steel engineering company to come up with this final third design. It's a Melan arch, so concrete, steel superstructure embedded with concrete, and it had very specifically located piers, and you can see them here. Right along the river, you're avoiding those fragile limestone beds, and the only way to do that was to create this curve. So you're going to be creating a curve in the bridge in order to make sure that the Falls of St. Anthony would be maintained. So why are people so interested in the design of a bridge? Predominantly prior to the early 20th century, bridges were designed largely for function, less for beauty. And there's some exceptions to that, but people weren't really thinking about that. But aesthetic consideration in bridge design was becoming a really important thing in the early 20th century, and it's largely due to the City Beautiful movement. And that's emerging from the 1893 Chicago's World's Fair. It's really bringing classical architectural styles forward and being championed for public spaces. So all public spaces, anything being constructed using public money, would be designed in a way that would be beautiful, classical, harkening back to a period where the Greek and Roman architecture, where people are just really feeling democracy. And there were a number of places within Minneapolis where you saw that come forward in public buildings. Gateway Park is an example of that. Oops, sorry. So what's the solution here? We've got Melan reinforced concrete bridge, right? Kaplan's solution is to avoid that fragile limestone, but it looks really nice and the public is very happy with this. It is embodying the classical revival style and that world exposition style that's coming out, and people were really, really excited about this. This is Chris and I's favorite quote out of a newspaper article. Stone arch construction would have been impossible or exceedingly expensive. Steel bridge construction would have been awkward, kinky, and crude. There you go, Kaplan. Your bridge design was awkward, kinky, and crude, but with reinforced concrete, no trouble was encountered in making the gentle curves and creating a pleasant pleasing appearance. So here we are, August 1914, we start building the bridge over in the Mississippi. How did they do it? All right, to move materials and supplies over the river, construction workers erected timber towers that were rising 165 feet tall. And they were connected with a cableway that stretched between them. And on that cableway, they ran buckets, supplies, all sorts of things out into the middle of the river to those construction workers. Cofferdams were erected within the middle of the river or wherever they needed a pier, and they built those down into the riverbed, secured them in the riverbed, and then from there they would support those arches. This is a really wonderful image coming out of the 1915 Engineering News. It's a news article, and it shows you, we saw it before where you saw the location of those different designs, but here in this bottom part of the image, you're really seeing how those timber tower structures stretch that cable all the way across the Mississippi. And then how they built and brought in those supplies. They had an actual rail line that came in, had a mixing plant. They brought their rock in. They did all of their mixing in batches right there on the side, on that east side of the river, put them in those buckets, sent them over the river into those locations that were where things were being constructed. Here's some great images from our historical society and construction of the cofferdam, construction of timber towers, and how they dewatered those cofferdams. Work was year-round. They didn't stop. They started in 1914 and continued through 1918 in the sleet, snow, and very, very bitter cold of Minnesota. And they did that. They were able to, make their concrete mix work by heating the sand, heating the water, making sure their Portland and all of their superstructure was warm to maintain all of those consistencies they needed. Couple of other images here. Bridge falsework was erected over the concrete piers to build those steel arches that then would be encased in concrete. Initially, it took crews 1 day to move falsework between the different sections, but by the end of the project, they were able to move that falsework in 2 hours and 40 minutes. So they found a lot of efficiency. Here's a wonderful image here that you can see one of those concrete ribs has been constructed and they're moving on to the second one. Each span has 3 concrete ribs. So you can imagine moving that falsework 3 times and then moving on from there. From those falsework, those open spandrel, the columns would rise up from those arches and the columns would then support the bridge deck. Opening day was June 14th, Flag Day in 1918. City Council asked all of the community to come out and celebrate, and all of the schools had their students come out as well. 4 years to construct that bridge. Here we can see a 1920s postcard that shows the bridge, those arches, the open spandrel columns there. You can see the overlooks. That was a key part of this design, this classical design. These are overlooks that allowed pedestrians to walk along the sidewalk, stop and view the beauty of the falls, view both sides of the river, view downtown. You can also see here in this image the streetcar line that would have come down the center of the bridge. That classical revival detailing here is on full display. It is very apparent in the piers and all of that ornamental detail there, as well as the bridge railing. The light posts, the light standards were quite unique, specialty design for this particular bridge. And at the very top, this is where the streetcar line electrical wire would have been connected. So it would run down the electrical line, would run down the middle, and then would be supported on the tops of these rails. The bridge legacy, this is an incredibly important bridge to Minneapolis history as well as Minnesota engineering history. It was the precursor to several open spandrel concrete arches that were erected within just the Twin Cities over the course of the next, 10 years. All of these are a great example of the design style, but Third Avenue is the one that set it all off. And then there were several updates over time. The railing was changed out in the 1930s to what we have there today, which is more of an Art Deco style, the aluminum panels with concrete pilasters. The streetcar was removed in the 1950s after the just decline in streetcar usage and the more popular way to travel by automobile. And then in 1979 and 1980, there was a large remodel that was that the Minnesota Department of Transportation did on the bridge. And Chris is going to talk a little bit about, the result of that rehab and how we had to come back here in 2023. So Chris, would you be willing to tell us all about the 2023 rehab?
Yeah, absolutely. So we started our project in 2020, and it really stems from just deterioration of the structure over time. It's you know, roughly 100 years old at that point, a little over 100 years old. The last major rehabilitation was, you know, 40 years prior. So the original construction and the rehabilitation construction from the 80s starting to deteriorate, and that deterioration is getting kind of advanced. So at the end of the day, the engineering need here is to go out there and make some repairs to keep this structure in service. Of course, the wrinkle with this particular project is we're dealing with a historic structure. It's designated. It's identified as a piece of you know, a cultural resource. So we have an obligation to make sure that the work that we do is not detracting from its historical significance. Interestingly enough, you know, a lot of the techniques that are used in modern construction are very similar or the same to those techniques that were used when it was originally constructed. At the end of the day, the basic physics of a bridge and construction don't change. Technology changes, materials change, our ability to execute that work changes, but the basics of physics don't. So a lot of those similar techniques exist today as they did when this bridge was constructed. In some of these photos, you can see we've got cofferdams in place. That's to exclude water from the area where we're pouring new concrete. That concrete needs to cure before it's inundated with the water from the river, both to gain its strength and to avoid losing materials during that curing. So they dealt with that in the early 19th or 18th or 20th century, excuse me. And we were dealing with it in the early 21st century, just the same. So we built cofferdams out in the river to be able to go out and pour new concrete and make repairs just like they did when they originally built it. We still use cableways. We didn't on this particular project, but the Pat Tillman Bridge out by the Hoover Dam is an example of one that was built in the last 10 years or so and used the cableway over the gorge. So that's a technology that's still in use today. We didn't use it in this case. A big difference between the 2023 project and the original construction. Of course, the city has grown up in that time. So properties that were previously industrial uses have been repurposed for recreational or residential or business, and they're not available to us today the way they were at the turn of the century when the bridge was built. So our techniques changed a little bit in that regard, but we worked throughout the winter. We had some of those same challenges. Again, we're trying to rehabilitate a structure here and honor its history. So the way in which we prosecute that work, we put a lot of time and effort into making sure that we weren't going to induce new damage. We weren't going to detract from that history and try and extend its service life. We brought in some new innovations. You can see in this picture, we put quite a bit of time and effort into a corrosion protection plan. A lot of anodes, cathodic protection in this project, and that's because when we look at a historic structure, it's protected by federal law, but beyond that, you have elements of that structure that are really central to its significance, its historic significance. And the Melan arches are one example with this structure of a character-defining feature and something that really requires attention to detail in its rehabilitation. One of the things that we ran into here is we're replacing the columns, and the way that those columns attach to the arches is a critical item for the engineering of the structure. It has to be robust enough to withstand all the forces that it's up against. But we are blending our modern codes in this new construction with in situ materials and an in situ design. So one of the problems that we ran up against was, how do we anchor these new columns to the existing arches without damaging that historic legacy? And so we essentially bring in new reinforcing steel. We anchor that into the arch. But from a design perspective, we needed to have a certain amount of capacity out of that reinforcing steel. And our modern codes, there's the depth of that reinforcement plays into the strength that we see. And we've got complicating factors with the existing arches. There's steel and structurally significant materials there that we have to avoid. So we had to come up with a pattern for these anchors. We had to make sure that we weren't doing something in the installation there that would create or would detract from the historic significance. So we utilized a novel theory here, a deep anchorage theory is what it's called. And so essentially, to get away from the limitations of traditional chemical anchorages, we drilled deeper. And what that allowed us to do is fully develop the reinforcing steel without having to through drill or go all the way through these arches and pin from the backside. That would have represented an adverse finding or an adverse impact to the historical significance. So that's one example, or another example. I have a little video here I'd like to show. It helps show the scale of the project during construction, but also points out one of the really big challenges that this project presented, and that's access. So you can see here, again, we've got the beginnings of some cofferdams going in and cofferdams coming out to dewater. We have these suspended platforms from the arches that provide us access to work on the structure and also capture materials that we're taking off of the bridge. You've got these cranes. One of the challenges here is loading and unloading the bridge. We can't do that asymmetrically, or we're going to induce new damage into the structure. So we utilize tower cranes in this case. Those red cranes, they come up out of the piers. So that way we're taking the arch ribs out of the load path. And that allows us to sequentially remove materials and place new materials back and ensure that those arches aren't loaded asymmetrically during construction, thereby, again, inducing damage. We have temporary bridges out there over newly reconstructed portions of the superstructure that allows access during construction without a deck in place. So a lot of different things, a lot of different unique problems that we ran up against, but at the end of the day, again, we have an objective to meet, which is to extend the service life of this structure, keep it in use, keep it in its current use. That was an objective that was identified well before the project came along, when we're looking at this from a historic resource perspective. But also, the grand scope, or the big scope of the project, replacing the deck, replacing the columns. We had the opportunity to really touch every part of the bridge, take care of any deterioration we found, and address the primary drivers of deterioration. So thermal movement of the bridge had started to kind of tear parts of it apart, and we were able to re-articulate the bridge so that it expanded and contracted appropriately without damaging itself. Management of water from the deck. In northern climes in Minnesota, the number one cause of premature deterioration of concrete is chlorides. They get into the concrete and they initiate corrosion of your reinforcing steel. So the old bridge had about 36 expansion joints in the deck. We were able to knock that down with our re-articulation to about 14. So those are all points at which water can move from the deck, carrying salts and chlorides down to the superstructure and the substructure below, inducing damage there. So the scope allowed us to really address those things. It also allowed us to take a hard look at the aesthetic details that were present during its initial construction and its period of significance, and bring some of those back, some of those things that were lost over the 100 years of use and refurbishment, and really, again, try and pay homage to its history, treat it the right way, and extend its service life well into the future.
Thank you, everybody, for the chance to talk about this awesome structure. I'm really, really excited that it's rehabilitated, and it was a wonderful project to work with the MnDOT and the project engineers on. So this is Chris's contact information if you have any questions about the 3rd Avenue Bridge.
Well, thank you, Katie. Thank you, Chris. And I understand, Chris, from our previous conversation, that you really had to make sure that Katie was happy, right? Because she was the historical guru on this project.
Katie was a tremendous resource to the project. I would say, when you're dealing with a historic structure, there's federal protections involved in the United States. We have laws that protect historic properties, and I'm an engineer. I'm not a historian. So that's a big hole in my knowledge base when it comes to a project like this. And Katie was central to making sure that we did this in the right way. You know, the Department of Transportation here in Minnesota is committed to long-term preservation of the structure. We have legal agreements in place that say this is one of 24 structures in the state that we are taking care of in perpetuity. And that helped be a focal point for the project team to ensure that you know, we're not stepping out of bounds in the way that we treat this structure. It represents a commitment and again a focal point for the project team to coalesce around and to say, this is our objective, is to take care of this structure, not just from a material standpoint, not just from an engineering standpoint, but from a historic standpoint as well. So you know, Katie's role was, we wouldn't have been successful if she wasn't a part of our team. So
all right. Well, Alicia Svensson, if you're on, what do we have for Q&A right now?
Yes, we have one question in the Q&A, and it's for Chris and Katie. Asking sort of if you can expand on what you mean by fragile limestone when you were talking about the crossing site.
Sure, yeah. Yep.
Katie, can you pull up that engineering record, that photograph or drawing?
Sure, give me a second.
So one of the things that's really interesting in Minnesota, in Minneapolis in particular, with the history of bridge building over the falls of St. Anthony and that area, and the amount of industry that had taken place in the beginning years of the city of Minneapolis, people started to identify fractures in the limestone of the bedrock at the base of the river. So underneath the water, the geology of the falls is you have a limestone cap that is highly resistant to scour from water, but it sits on top of about 16 to 20 feet of sandstone, which is highly erodible. So from the time that the glaciers in this area started to recede 10,000 years ago to today, the falls had actually moved upstream an average of about 4 feet a year in the latter years because of the action of that water coming over the falls and eroding the sandstone below, leaving a cantilevered limestone shelf that eventually broke under its own weight.
Can you see this?
What you see in this photo is that the cross-hatched areas are actually fractures in the limestone that were identified by industry, engineering, a variety of different sources in the years preceding construction. So these are actually mapped out, and you can see it in the engineering drawings for the structure. So that's where you see they're even identified with years. A break of 1878, first break in limestone, 1869. So these are when they're identified, and that represents a weak point in the bedrock. And these are all these piers are built on what's called spread footings or shallow footings. So they bear directly on the bedrock. Whereas, you know, a lot of times in modern construction, I think in Ulrich's presentation, I think I saw some, or maybe it was Robert's, but there were piling that were driven underneath the piers down. Those are deep foundations. This bridge is built on shallow foundations, so it sits directly on the bedrock. So the condition of that bedrock and its surrounding area becomes really important structurally. And that's where knowing where these breaks are, Kaplan understood we can't put a pier where the team from New York has identified a pier to go because we don't have the support on the riverbed to allow that pier to be there. So that's what we're talking about when we talk about the weak spots in the limestone is bedrock conditions that preclude a support being placed on top of it.
Okay. Alicia?
Then I don't know if we have time. I'd actually love to abuse my position as the Q&A moderator to ask a question for Robert, which is I was really interested in the sort of the chain links used in the Newburyport Bridge versus those flat bars you were showing us in those later bridges from the UK. And I wondered, is that a sort of innovation that improved on the chain link technology, or are they sort of different versions of a similar technology?
Great question. Thanks, Alicia. I would say a little both. I think the chain link, why it dominated Newburyport, was they probably didn't have the facilities to make those bigger iron bars, the flat bars. And also it's a scale issue. The chain link, the few chain link bridges that there are were smaller spans. Even the one that had multiple spans, the actual span was shorter. The ones in England were much bigger, and they were advanced in their industrial revolution production of iron components. So that's my theory onto why each of those. But what I find interesting is that they're going on at the same time, but it has to do more with context, I think.
Hmm. I think Tower Bridge in London is also the same type of construction. That's the one that's often visited
Yes.
and photographed, I might add. So very interesting. We do have another question, or maybe it's just a comment. I can't quite see it in the chat here, but from Bayu Tekle. Just to hear from such immensely enriched, Alicia, can you see that? Here it is. Okay, I got it. Hear from such immensely enriched minds, what is the biggest bridge in the world and USA that you want to talk about? Or a little more to say about. What would that be?
I'll jump in with my opinion. And it's interesting. The longest span suspension bridge in the U.S., to my knowledge, is still the Verrazano Narrows from 1964, approximately. And that's a long time ago. So the longest bridges in the world are being built in Asia. And my understanding is suspension-wise, longest span, now that's the distance between towers, is now over about 6,000 feet. So Verrazano is probably 4,000, so 6,000, which is over a mile.
Yeah, interesting. So, Ulrich, can you clarify again how many men, I'm assuming it was men, maybe they didn't allow women to push those bridges, those levers across. So it was like, if I understand correctly, it was one bar across the span with these sort of ratchets, sort of like a ratcheting device to take it mechanical advantage of pushing it. I think you said 13 centimeters with each push. Is that right? You got to.
Moment. I'm just looking. It was 10 centimeters with each lever moving.
Wow.
10 centimeters and 44 meters a day.
Wow. That's a lot of men, a lot of hours, probably a lot of working just to go 10 centimeters.
All the time on top, they changed the groups, you know. They couldn't work more than 8 hours or 10 hours a day. So they had 2 or 3 groups to move.
Wow, that just blows my mind. Just the creation of that device here. And more recently in Minneapolis with the 35W bridge replacement, you know, it's sort of a similar concept, except now we use post-tensioning to build from each side until we can connect into the middle. That's sort of the adaptation of that technology and doesn't maybe require quite as many men pushing so hard.
Well, I think one of the things, Peter, and forgive me for going down a little bit of a rabbit hole here, but we talk about bridges, we talk about building, and we talk about the brawn that's required to build them. That's kind of the theme of our presentation here today, right? One of the things that strikes me in this conversation is the economic forces that are at play, right? And I'll use the United States, our history with bridges as an example. Round about the mid 60s, the price of steel is overtaken by the price of labor. And what you see as a result of that is the type of bridges changes. So we're dealing with a different era here. Trusses are a prime example. Trusses are a really efficient design from a material standpoint. So you're using less steel essentially to span your span and carry your loads. Well, when labor becomes more expensive than the steel, the time it takes to assemble a truss now becomes an economic driver. So engineering at its core is about solving a problem with the least amount of resources that you can. And typically those resources are currency, dollars and cents, whatever currency you're using, right? So you got to buy the materials and you got to pay for the labor. Well, when that dynamic shifts, suddenly now we move into more girder bridges that are less efficient from a steel perspective, but more efficient from a labor perspective. So the context of this discussion is salient to that, right? We are now in an era where the price of materials is typically not your primary driver. It's the cost of labor, and bridge design has shifted accordingly. But all of these bridges that we talk about deal with a lot of human input, a lot of human effort to construct, because the limiting factor was more the materials than the labor.
Yep. I am, however, glad though that when Katie showed the different arched bridges and how they were influenced up and down the river, that the new 35W bridge sort of resembles a little bit of a streamlined arch that respected that as opposed to being a steel structure. So that was very telling. So Alicia, go ahead.
We have one more question in the Q&A. And it's again for Robert. It's regarding the Newburyport chain bridges. There was an image of the other bridge that seemed to show the center deck span as arched compared to the other flat deck spans. Was this an accurate rendering, and was this arch intentional?
Yes, that's a really good question. And we call that camber. So that slight curvature at the center of most bridges. And you'll note in a lot of those images, it was hard to discern. Camber in modern bridges is much greater. And I think that was a factor of the bridges that, they were still learning about. And it was interesting, if you looked at those original arch bridges, the timber ones, they were much more arched, but there wasn't a sense of the cambering necessary when you were suspending from a tensile chain. So very perceptive, whoever picked that up. That's an interesting point.
Okay. Panelists, do you have any more questions for each other after hearing these presentations?
No, I'd just like to say thanks to my co-presenters, and an observation just popped into my head recently, right now, is I don't know if this is intentional, but the bridge I talked about was primarily in tension. The arches in Minnesota were primarily in compression, and then we had that long span truss working in bending. So well done, Peter.
Yes, I planned all that. All right. Well, I just want to thank everybody for presenting today. This has been terrific. I really enjoy listening to this stuff, and I hope everybody else did. Just to the audience, thank you for joining us. I would like to invite you to become members of the Construction History Society of America. Just go to our website. You'll find a way to link in. But for that, I would just tell you, thank you, and enjoy this particular day in history.